Sir, we are live. Please start.
Okay, good evening, everyone. This is your course instructor, Polarization. I think this is just our second live session. So last time we had a session where it was really not interactive. So I think you had to just post questions and I would just address those questions during such a session. That's what happened last time, but I think NPTEL has actually opened things up a little bit so that we could be more interactive. So you could ask questions live and you could interact with me during this session. So I see only a few people that have shown up for now, but maybe more people will join. But nevertheless, I think even if you're watching it later, I would think that this is going to be a somewhat useful session for you. One of the key things that a lot of people are starting to wonder is how is this course going to end? What's coming up with the remaining weeks and how the final exam is going to be compared to what we have done in the assignments and so on. Right, so let me try to spend a few minutes addressing some of those questions. I think you are in week 9 now, so you will be getting your contents for week 10 shortly. And so up to week 9, I think we are discussing semiconductor detectors. So you'll probably be just recently aware of how a PIN photodiode works, how a APD works, and what are the typical characteristics of these photodiodes and so on. And I think we'll also be talking about a little bit about how to build a optical receiver based on these photodiodes. So that would complete our discussion on semiconductor light sources and detectors. So if you remember, we started with ray optics and then went on to wave optics and then electromagnetic optics, and then looked at the statistical properties of light, went on to look at the photon aspect of light, the particle aspect of light as well. And then we went on to look at how photons interact with atoms. And that actually, we were talking about absorption, emission, and so on. And then that led us towards the concept of amplifiers, optical amplifiers. We looked at erbium doped fiber amplifier as an example of that. And then from an amplifier, we started incorporating feedback. And then we started discussing lasers. We talked about 3-level lasers and 4-level lasers. Primarily, and from there we went on to semiconductor platform until I think week 5 or so. We were discussing about atomic systems. So with rare dope ions, how we are getting gain and so on. But beyond that, we started talking about semiconductor medium. Using the semiconductor medium for gain initially. So we were talking about how to make light emitting diodes and laser diodes. And lately, the last couple of weeks, we've been looking at semiconductor photodiodes, specifically this, like I said, PIN APD photodiodes. Now, what's coming up beyond this is we're going to try to see, so we know general properties of light. We know how to generate light, how to detect light. Now, next thing that we're going to look at is how to manipulate light, how to control the properties of light. And one of the key topics that we will look at next is actually with respect to light polarization, how we can manipulate light polarization to achieve different functionalities. And then we will look at how to control light using nonlinear material. So far we've been talking about only the linear aspects of propagation in terms of the light. But we considered all our medium to be linear, meaning for a certain intensity of light or a certain amplitude of light, you will get a certain response, and that actually, as you increase the amplitude, the response will correspondingly increase. That's the way we have treated all our medium. But as you keep doing this beyond a certain level of light, you will start seeing that the medium is starting to behave in a nonlinear fashion. And that aspect is what we're going to discuss in week 11 and actually 12. So we will look at what are called second order nonlinearity and then third order nonlinearity, and what are the different optical functionalities that we can achieve by manipulating light and manipulating basically or using these nonlinearities to achieve all these functionalities. Okay, so that's what's going to come up for the rest of the next 3 weeks or whatever you have left in the course. And then, of course, a lot of you would be looking forward to the final exam. You'd be wondering how the final exam is going to look like, and how do you prepare for the final exam. So let me take a couple of minutes to explain that. The final exam is going to be not very different from what you have been doing in the assignments. So you will be having assignments. So it will consist of 2 parts, 2 sections, if you may. The first section would have a lot of these multiple choice questions and fill in the blank questions, match the following questions, the kind of questions that you have been dealing with in the assignments. In fact, there may be questions directly from the assignments also. So that actually means that, you do want to make sure you are familiar with all the question and answers in the assignment. Maybe some of you are not able to work out the problem yourself, but nevertheless, if you are able to, look at the solution and understand the solution, that would be good, because that will be a very good preparation for the final exam. And I would, of course, encourage you to get on to the discussion forum and ask questions if you don't understand a solution or you don't agree with the solution. Those are things for everyone. If you can just mute yourselves, yes, that would be great. Okay. So, yeah, I was saying that even if you did not get marks for a particular problem, it helps to actually understand how that particular question is solved, because the same question you might actually face in the final exam. Okay, so please do take these assignments seriously and try to work those out. So that is section 1. That's about 50% of the questions. Section 2 is going to be a little more interesting, in the sense that, I will be asking you to put together a system altogether, right? So let's say you're building an optical sensor. Okay, if you're building an optical sensor, what do you need? You need a source, you need a detector, you need to understand the propagation of light through the sensing medium. You need to suppose the sensing medium is an optical fiber, you need to understand how light propagates in an optical fiber. And you may have to manipulate that light, you may have to modulate that light, and you may encounter nonlinearities in terms of the propagation and so on. So although the entire focus is going to be towards building a system, an optical system, I will be actually breaking it up into a question on transmitter, a question on receiver, a question on propagation of light in a medium. You know, the things that you've been looking at the different weeks. So you know, don't be fazed by the fact that you're building a system. I am actually breaking it down for you into individual questions. Focus on the individual questions. And those questions, once again, are the questions that you have been already seeing in the assignments. So, so it should not really be very different from what you have been trained on. Okay. So overall, I would say the entire paper would be like assignment type problems. Although, like I said, section 1 would be directly like, you know, what you have been looking at as assignments. Whereas in section 2, it will be more of a system design, which brings about, you know, this is the idea of the course. If you went back and looked at the learning outcomes of this course, one of the learning outcomes, one of the larger learning outcomes of the course is to be able to understand all these optical components, all these optical processes to the point that you can actually make decisions on how to build a system, design an optical system. Okay, so that is what the last section is about. But nevertheless, it's not, like I said, it's not something that is going to be totally alien to you, because I will break it down to a level where each of those individual questions are going to be, once again, like what you have been dealing with in your in your assignments. So before I move on, any questions about what I just now said? Any comments on that? You may unmute yourself if you have a question. Otherwise, we will move on to other things. Okay, so I gather that that part is clear. Like I said, we still have 3-4 weeks left in the course. So, you know, you could always, if you wanted to get back to me later on, you know, send a message in the discussion forum or something. You may feel free to do so. Okay. Now, I do see a message in the chat. Yeah, okay, that's nothing. Right. So let's move on to the next part. The next part is actually we had sent you a form, a Google form, and asked you to you know, fill out that form, ask us any questions that you may have. Okay. So let me go ahead and try to address those questions. And thank you. I mean, there are several questions here. So thanks for contributing to that. So the first question is, can we consider relative intensity noise the same as our short thermal and dark current noises, and how it is different from phase noise? Okay, so that's a good question. I'm not sure we discussed a lot about relative intensity noise, but I think I mentioned that as part of you know, our discussion on sources and receivers. So so maybe I can share my screen now and try to explain what this relative intensity noise is about. Okay, so any optical system, like we mentioned, is going to have a transmitter which is emitting light, and that's going to propagate through some medium, and you would have a receiver that's collecting that light. So when we talk about noise of the different types of noise that we encounter in an optical system. This is very, very important because the noise in the system is ultimately going to determine what is the performance of the system. So if you're doing communication, for example, I have my broadband coming through an optical fiber. The optical fiber is carrying information from my port towards the server and then on to you, as well as I'm getting feedback from your side to me. So the most important aspect of how I am able to receive that information is the signal to noise ratio, right? So what is the signal power to the noise power that I have? So if I have a signal that basically is looking like this, right? So then it's easy to make out that there is something at this level and there's something at this level. It's easy to make out that this corresponds to a 0 and that corresponds to a 1. Okay. But what if you have something like this, right? If you have a lot of noise in the same information, then it's not very clear, whether this one, whether it will be corresponding to a 1, whether if you sample at this point, it's not sure whether it's actually 1 or 0, and so on. So you might actually have a lot of errors in your detection. So signal to noise ratio is a key aspect that determines the performance of the system. Having said that, it's very important to understand what are the noise sources as far as your system is concerned. And we have just been discussing about semiconductor light detectors. And we have actually, just the last week, we have introduced concepts like short noise, thermal noise, dark current noise, which is actually just a variant of short noise. But all these are related to what's happening at the receiver. Now, could be some noise from the transmitter side also. And one of the key noise sources there is what is called this relative intensity noise. So that is what I think the question is about. How is this relative intensity noise different from all these? All the other noise sources that we are discussing are all at the receiver, but this is at the transmitter. And this happens because of the fact, although, as a transmitter, you are trying to, like, if you look at the power as a function of wavelength, you are trying to transmit at a particular wavelength, right? And you would expect that this particular light has fairly high coherence, so that you can actually not undergo a lot of dispersion and so on. It's narrow line width and highly coherent. But what happens typically is, along with this light emission, let's say it's a laser emission, you also have some extra emission. Okay, so what is this? This is actually what you call as spontaneous noise, right? Whereas this is typically due to stimulated emission. So why I'm calling spontaneous emission as noise? Because spontaneous emission does not have a consistent frequency. It does not have a consistent phase, and it does not have a consistent direction, right? So when it actually gets emitted, this is actually quite random in nature. Okay, whereas the stimulated emission is relatively more deterministic because of the fact that you can say it's actually at around a particular wavelength, and it's on the average you can say it is going to have so many photons within a time slot. So you may have this when both of these are emitted, and it's inevitable, right? So whenever you have a laser, you are primarily getting stimulated emission, but it's inevitable that you have a little bit of spontaneous emission also. Okay, and that spontaneous emission is having a random phase, and so when it's actually beating with the stimulated emission, the beat component will be quite noisy because the phase can be the same, in which case the photons add, the strength of the fields add, or it could be out of phase. It could be say pi out of phase, in which case it will cancel the field of a stimulated photon. So you would have in general the light that's coming out, if you're talking about the intensity of light. This is light intensity as a function of time. We are expecting the light intensity to be like this. Let's say, let me just be consistent and try to use the blue color here, right? So you want constant intensity, but because of this spontaneous emission, you would have a certain noise around it, right? So certain variability in terms of the intensity of light. So that variability is what we are calling as relative intensity noise. Okay, so to answer the question directly, relative intensity noise is originating from the transmitter side, whereas all the other noise sources are at the receiver side. I think Kushagra is the one that asked this question. Is that the answer you are expecting, Kushagra?
Yes, sir. Thank you, sir.
Okay, great. All right. And then, of course, there was also this question about, what is phase noise? Now, phase noise corresponds to, whenever you are receiving a light wave at the receiver, right? You are expecting ideally a monochromatic wave, but it's really not a monochromatic wave because there is a finite range of frequencies that are being emitted. So there will be some polychromatic aspect of light. But anyway, that will have a certain phase. So this can be expressed in terms of phase as well, where it goes from 0 to 2 pi. And that phase may not be deterministic because of, a simple thing is because of the polychromatic nature of light, different frequencies within this band itself will have a different phase that would have accumulated before it reaches the receiver. So the phase of the received light is uncertain. So that is what we call as phase noise. However, that phase noise is not going to be an issue for us in most applications that we are talking about in this course. It's because of the fact that typically, whether you consider a communication system or a sensing system, you're typically looking at changes in the amplitude of light. So phase noise is not an issue. Having said that, I would also say that some of the state-of-the-art communication systems, which are called coherent optical communication systems, rely on the phase of light, and their phase noise can be important. But like I said, this is actually a very fundamental course, so we're not going to go into much details of that. But if you take, say, a course on fiber optic communications, or any optical communication course in general, you will be learning a little more about what is the role of phase noise in the overall performance of the system. Okay, so let us move on. I'll just go back to the other questions. The other question is, why are we considering impact ionization as a serial process and impact ionization as a statistical process, or both should not be the same? So what are we talking about here? Okay, so let me just come back and address that. So impact ionization, happens in an avalanche photodiode, right? So what is the construction of an avalanche photodiode? So we've been looking at that just lately, I think the last week. We take a PIN photodiode, but along with the N, if there is say a P plus layer added, okay. So whenever you have a P and I interface, you will actually have some majority carriers that are holes that are moving out of this region. So that will be depleted of the holes. So you'll have some fixed negative charges. And similarly here also there will be some negative charges. And in the N side, you will have a depletion of electrons. So that will leave behind positive charges. So when you connect this photodiode to an external circuit, typically we tend to reverse bias the photodiode so that you can improve the response time of the system of the photodiode. So if you connect it to a reverse bias, what will happen is the fields will actually will drop only in those regions or will exist only in those regions where you have this these charges, right? Gauss law tells that the charges, the presence of charges implies that you will have some fields. So when we look at the voltage across this structure, that voltage drop will be something like this. And in this region, it will be like a fairly high voltage drop because you have a sudden change in the charge density from negative to positive. Okay, so there will be a very large field over here. And if that field is beyond a certain threshold for this impact ionization process, then what happens is you have these charges, let's say in this case, whenever light is coming in, it's generating electron hole pairs. And in this case, the electron would go this way and the hole would go this way, right? If there is a absorption that happens. And the electron, as it goes across this region where this is what we call as a multiplication region, where when it goes across this multiplication region, that electron would have, and the influence of this very high level of field, electric field there, it will get accelerated and it will cause this impact ionization events. It will basically bounce off these atoms there, and then it will generate secondary electron hole pairs. Okay, and that is what we call as impact ionization. So this electron is going to generate an electron hole pair, and once again the hole will move this way, the electron will move this way, right? And then this electron can cause an additional electron hole pair, and so on. So once again, the hole will move this way, electron will move this way, and so on. So it can create a avalanche of impact ionization events. Okay, but this event is first of all serial in nature, because one is going and hitting the other, and then is causing a sort of a ripple effect. And so it's multiplying in a serial manner. Okay, so that's what is saying it's actually a serial event. but it's also a random event, meaning it is not like every electron that's going into this region will generate, say, 10 electron hole pairs. It might at some point generate 5 electron hole pairs, or at some point it may generate 12 electron hole pairs, and so on. So it is not a deterministic process, a random process. So it's both serial as well as random process. The serial nature comes from the fact that it's actually a ripple effect, but the randomness comes from the fact that you cannot tell with certainty that every electron is going to generate so many electron hole pairs. Okay, so hopefully that answers the question. Kushagra, you have a comment on that, or?
No, sir, I understand.
Okay, thanks. Okay, let's move on to the next question. So, is an EDFA a laser without feedback element? So that's a slightly twisted way of looking at it. I would rather say that a EDFA or any gain medium with feedback makes a laser. Okay, so there is a cause and effect. So laser is not the cause, laser is the effect. The basic cause of a laser is the amplification aspect of it, right? So you start with an optical amplifier, and then you add this feedback on either end, and then you get a laser. Okay, so instead of asking the question this way, would you'd rather want to ask, is a EDFA with feedback element make a laser? And the answer would be yes. Do you understand?
Yes, sir.
Okay. So then there is another question from Tripathi, Samarth Tripathi, I think. So the gain medium which we talked in laser are Fabry-Perot or an optical fiber. I think the question is maybe not framed correctly. Maybe what is being referred to is actually the experiment that was done a few weeks ago when we were talking about lasers. We were actually having a ring cavity, right? So if I just go back and try to draw that. So normally we talked about this cavity where you have a certain gain element, and with feedback at both ends of the gain element. So these are reflecting elements. So there will be like multiple round trips. And if these mirrors are parallel to each other, this is what we call as a Fabry-Perot cavity in general. But if it's making a laser, we call it a Fabry-Perot laser. Okay. So that is one of the common laser cavities that we discussed, and it's one of the more common laser cavities that you see in general. But when we were talking about lasers, I actually mentioned about this other cavity that could be that could make a laser as well. And in this case, we were considering a erbium doped fiber amplifier, the output of which was looped and fed to the input. So in this case, the fact that you have a looping of the output to the input was making a cavity, right? So that there is a certain round trip associated with this. And this type of laser is actually based on what is called a ring type cavity. The beauty of this ring type cavity is it doesn't require any mirrors. So you can actually just feed the output back into the input. So, so that way it's unique. But there are reasons why you may want to have a mirror, because you can If it's an external mirror, you can change the mirror and you can change the properties of the cavity a little more easily than changing this ring cavity. But nevertheless, these are two different cavities, and with both of these, you can have a gain element, and using that gain element. So in this case, this is your gain element, and using that gain element with feedback. In this case, the feedback is coming from this. Here, the feedback is coming from these mirrors. So gain element with feedback is what is making your laser. Okay, so hopefully I answered that question. Then the next question is, do we send signal photons immediately with the pumping or a little later after some buildup? Okay, so that's a good question. So let's come back here and try to understand. So I think the question is in reference with an optical amplifier. Let's say once again, since we're talking about erbium dope optical amplifier, let's say this is like a erbium ion that we have, and we are pumping with let's say a 980 nanometer photon. Okay, and what will happen is this will just non-radiatively relax here, and it will go to a metastable state where the lifetime of the state is actually relatively long. So it will go there, and from there you might have this stimulated emission. Right, that's what we talked about in the class. So of course, to get a stimulated emission, you need to stimulate with a photon corresponding to this energy difference, and then you can get two photons out with the same properties. Right. So that is what we are talking about as far as the an amplifier is concerned. Now the question is, do the pump photon and the signal photon. So here we're talking about pump photon coming in and it's causing this inversion, and signal photon causing this depletion and a stimulated emission. Do they have to be at the same time, or does the signal photon here, does the signal photon have to be at a different time compared to the pump photon? Right, that's the question. I would say yes, of course, the signal photon would not be able to cause stimulated emission unless we have this inversion or this excited ions already in place, right? Without that, stimulated emission cannot happen. Okay, so from that perspective, yes, the pump photon has to be coming in first and generating this inversion or generating a certain population in the excited state, and only then you could have stimulated emission. But do you have to, like, say I flip a switch, I turn on the pump, and I have to wait for like a few minutes and before you turn on the signal? Not necessarily, because this absorption event is sort of instantaneous. The moment the photon goes into the gain medium, it will, if it sees an ion in the lower energy level, and if it's got the right energy difference, it will immediately pump it to the higher energy level. And from there, it actually takes only say something in the order of 100 microseconds to actually get to this state. So it's within that time scale, within tens of microseconds, you have an excited ion. So you could immediately achieve stimulated emission. So you don't really have to time it that way. And it helps actually to delay the signal photon so that you can have several number of uh, uh, the ions in the excited state, but it's not a necessary condition, right? So did I answer your question, Kushagra?
Yes, sir. Thank you.
Right. Well, thank you actually for so many questions and good, interesting questions as well. So let's move on. So the other question that I see here is the emission cross section that we calculated was for pump frequency or that of signal photon flux wavelength. So that's actually a very twisted question. I think what this person means is probably the signal wavelength or frequency. Flux is actually corresponding to the rate of flow of photons with respect to number of photons per second. So that actually is not an issue here. I think what they meant is actually whether it is for one wavelength or the other. Yes, the emission cross section that we are looking at is for typically we are interested in is what is the emission cross section for the signal photon. So if I just go back here, so I'm trying to get gain at this wavelength. So I am interested in the emission cross section sigma E as a function of wavelength corresponding to the signal wavelength, because that's where I'm trying to get gain, right? And of course, in erbium dope fiber amplifiers, we say that the emission cross section is something like this. It becomes significant around 1520, and then it has got a long tail over here, but somewhere around 1560, it starts going down. So yeah, so that's what we are interested in. We're not interested in the pump emission cross section, which actually, by the way, is very low. You're pumping somewhere over here at 980 nanometers, right? Sorry, I didn't mean to write that way. So there, the emission cross section is very low because of the fact that this particular level is actually very short-lived. So it cannot actually stay there and emit. So it would non-radiatively relax to this other level from which this is much more likely. So the emission probability at 980 is much lower compared to what you have at 1550, around about 1520 to 1560. Okay. So that's the signal cross section is what we are interested in. Of course, there is a possibility that the signal photon itself may actually get absorbed. So I should probably draw this with a different color so it's very clear what I'm drawing. So this, I said, is corresponding to the emission cross section at around 1550, around that band. But you also have an absorption cross section, which is actually significant around 1480 or so, but then it becomes very small as it goes to this these regions. So this is sigma A, and this is sigma E. So I'm just looking at cross section. So like that. So there will be a finite absorption cross section at the signal wavelength also, which is something that we want to be aware of, because that is actually something that determines your gain, right? Your gain is actually corresponding to N2 sigma E minus N1 sigma A, right? Sigma A at the signal wavelength. Okay, so that is what actually determines the gain, and it helps that the absorption cross section is relatively low in these regions. So in fact, as you go to longer wavelengths, you can approximate that the absorption cross section is 0, and then what is actually dominant is actually the emission cross section in those regions. Okay, but yeah, we are interested in just to answer the question here, we are interested in the emission cross section at the signal wavelength, and of course the absorption cross section at the signal wavelength. Emission cross section at the pump wavelength is not so important. Okay, so what the next question is, what is the use of variable optical attenuator in producing laser, and how is that different from what we used in FVG? Okay, so that's a good question. So let's go back to this cavity. So I think this is in relation to what we discussed as far as the ring laser is concerned. We considered two different conditions. One in which we had a variable optical attenuator, okay, and the other cases where we actually used a circulator here, and we used a FVG. So what is the significance of these two configurations is essentially the question. So let me try to answer that. So once again, if we go back and look at laser theory, right? So we talked about the role of gain versus loss, and that's what determines where the oscillation is, right? So the gain is actually something like this. For let's say this is for erbium, okay, and the loss may be something like this. Let's say this is your loss line, okay. So what we talked about was where the gain meets the loss, okay, that's where you will have the laser emission. And of course, there was some nice questions about this entire process in the discussion forum. So I was explaining why just having a large gain in certain wavelengths, that is not enough to make the laser oscillate at those wavelengths. It actually depends on the saturation of the gain medium. Higher gain also means that more saturation, more number of photons is building up in the cavity at that wavelength, and as an effect of that, there is more saturation of the gain. So finally, where the gain meets the loss is where the oscillation is. And typically, I was saying it's typically is where it meets the gain at the longer wavelength, and that is because of the fact that your absorption cross section is lower as you go towards longer wavelength. So it's almost zero at longer wavelengths, and because of that, there is very little loss for those photons that are circulating the cavity, and those are likely to survive the cavity more than photons at these wavelengths. Okay, where the loss, I mean the absorption could be significant. Okay, so now coming back to this question, the question is, what is the role of the VOA? The VOA in this case actually is allowing us to change the loss inside that cavity. By changing the loss in the cavity, we are actually moving this this level and moving the point where the gain meets the loss. So you can, so what we were demonstrating as part of that laboratory experiment is that you can tune the output emission wavelength of your laser by changing this loss using the VOA. Okay, so that was the role of the VOA. The VOA in this case was used to change the wavelength at which it was oscillating. Now, let's go to the other part where where an FVG can be useful. An FVG is useful in making sure at any particular operating condition only one wavelength is oscillating, and that is because of the fact that the FVG has a loss spectrum like this. So at one wavelength it will have very low loss, all other wavelengths it will have very high loss. Okay, and that means that the gain meeting the loss condition is satisfied only at that wavelength, and this wavelength is called Bragg wavelength. So in this case you can get a very stable oscillation at only one wavelength. We saw that in the other cases without the grating, we saw that the laser was oscillating at different wavelengths at different times. It was not very fixed. It was fluctuating around, and that is because of the fact that wherever it meets the gain versus loss condition, there is a possibility that laser oscillation there. So it was shifting across this entire band here. But with the Bragg wavelength, with the Bragg grating, what we are doing is we are introducing loss for all other wavelengths except for a narrow band of wavelengths, and then that means that only at those wavelengths the oscillations happen. Okay, so hopefully that is clear. Any questions about this?
Sir, is it easier to use FVG?
It's not a question of being easier, but of course, using a FVG means you are actually having this extra components that you have to incorporate inside the cavity. So that way, you can say it takes a little more effort, but if you want to get a performance out of the laser where the laser emission wavelength is rock solid, it's only at that one particular wavelength all the time, then yes, you have to use a FVG or some other device where you can get this sort of a loss spectrum. Okay, so yeah, those applications that you have to go for that element. Any other questions about this? I'm sorry, I'm drawing so many things in the same page. It's a little intentional because of the fact that all these concepts are connected with respect to each other. So even though they were different questions, because they are connected with each other, it's easier to understand everything if it's all in one page. Just excuse the mess. Okay, let's go to this other question. During pumping, the atoms are excited to metastable states, or the excited state first, or it depends upon the pump wavelength like 980 or 1480. So I think we already discussed that. So yes, in the case of erbium, we are actually pumping it to a higher energy level, and from there it's going to that excited state, and from which you are getting the stimulated emission, the gain. But of course, we can choose to pump at, because this energy level here is not a single level, it's actually consisting of multiple levels here. You can choose to pump at this wavelength, which is basically this is 1480 nanometers, right, around this. So you can choose to pump at that wavelength and get your emission as well. And it's just that 1480 nanometer lasers are not as easily available or as not as cheap as 980 nanometer lasers. So most applications use 980 nanometer lasers for that. But yeah, you can pump at either wavelength. So the metastable state have larger, I think what they meant is longer lifetime than the lower energy level. Yes, that is almost an essential condition because only if this metastable state, this is longer lifetime tau, only if there is a relatively long lifetime, then only you can actually have a significant accumulation of ions and significant accumulation of population inversion, and then that actually determines how much gain you can get, right? The gain coefficient is actually dependent on this. Okay, so yes, that is a essential aspect of this, that it's a long lifetime. Now, does it have to be longer than the ground state? Well, the ground state is the resting state, right? In this case, so in this case, you know, you can say that the ground state, the atoms are like there for a much longer time because it's one of those happy orbitals. I mean, these I mentioned before that these corresponds to different orbitals of this particular atom, and so it actually is one of the allowed orbitals. So it loves to stay there, you know, for how much ever long. It's only a question of how to get that excitation, and so in this case, the upper energy level, longer the lifetime, better. Now, there are lasers, for example, I'll talk about neodymium laser. In neodymium, you have a pumping that happens over here, some non-radiative relaxation over here and some non-radiative relaxation here, and this is where the signal transition is, right? So this is where you can get stimulated emission. Okay. In this case, it is important that if you call this tau 2 and this is tau 1, it is very, so to get population inversion, you don't want ions sitting here. So you want them to quickly relax. So tau 2 should be far, far greater than tau 1, right? So in this case, you want to have a lot more ions that are sitting in the excited state with respect to the lower energy level. And you know, that's when you can actually have more population inversion. So this, I would say, is generally true. But of course, in this case, if you are going back to the ground level, that cannot be true because in the ground state, it can stay for a very, very long time unless it's excited by the pump photon. Okay. Any questions about that? Okay, move on. I think this person, Swaminathan, well, he just mentioned that he needs to talk to me about something. Swaminathan, if you're there, we can probably meet after this session. You can stay back. Okay, so that's all the questions that I can see. Let me just check if there is any question that's posted in the chat. No, I don't see any other questions here, or maybe there is one. Okay, is it the amplified spontaneous emission goes into the feedback for laser generation or the spontaneous emission? Okay, good question. So let me just quickly address that. So initially, when you start a laser, right, you start pumping. So you are essentially bringing in your pump radiation into your amplifier. You're starting this process here. And initially, when you're doing that, you want to generate this inversion, and you want and for the simulated emission to happen, you need to have this signal photon coming around. So where does the signal photon come from? The moment you start the pump, you turn on the pump, the first thing that happens is you have spontaneous emission that is circulated across this. And of course, the spontaneous emission itself may be amplified within the EDFA. So you can, in general, it can be called as amplified spontaneous emission. So that spontaneous emission is going to be the seed for stimulated emission that's going to happen among from some subsequent round trips. Okay, so this certainly is the seed for the stimulated emission, and then only you can actually get gain, and then we can talk about overcoming the loss, and then we can have laser oscillation. So certainly that spontaneous emission has a very important role to play in the operation of a laser. And it's just that, I mean, connecting our thoughts back to this, is just that once the laser starts, you want as low spontaneous emission as possible, because spontaneous emission at the end of the day is a random emission, and it will essentially cause noise. So you want this to be as low as possible. Okay. So with that, I would say we have discussed all the questions that have come up. Thank you for all those questions, and thank you once again for all the questions that you are raising in the discussion forum. I think that is very, very important. It's not just for your own understanding, but you are helping others understand some of these concepts as well. So I really, really appreciate those of you that are contributing to questions there. Please keep that coming. I think it's going to be very, very important the next few weeks that you get all your doubts clarified before the final exam. And of course, in any way, it's not about marks, it's about the knowledge that you gain through this course, which will enable you to take other courses and make a career out of this photonics field. And so from that perspective, just keep asking questions, and we will try our best to answer all those questions. Okay. So with that, let me close this session, and thank you for your attention. Balaji, you can turn off live. Maybe the person is not around, so maybe I have to leave this session. But Swaminathan, are you there? Mr. Swaminathan? I can hear some noise from your end, but not your voice. I would suggest that you just send me an email, and we can try to, touch base with each other through that. Okay, my email address is balajis@eeitm.ac.in, and it's easy to figure that out if you just do a Google on my name. Okay, so thank you guys. Take care, everyone. Bye.
புரிஞ்சிச்சடா? நான் கூப்பிடுமா அவர் கூப்பிடுமா எனக்கு தெரியல. யாரு தெரியுமா? இதுதான் நான் போய் படிச்சு சொன்னேன். ஹாஸ்டல்ல வேணாம், வீட்டுல எங்க கூட இருன்னு சொல்லி கேட்டியா? வீட்டுல இருந்திருந்தா